Hi, everybody. Please join me in welcoming our next set of speakers, Dr. Marwin Segler and Dr. Timur Madzhidov. Marwin is a team lead at Microsoft Research AI for Science, working at the intersection of chemistry, drug discovery, and machine learning. Prior, Marwin was at Benevolent AI and received his PhD in chemistry from the University of Munster. Marwin pioneered machine learning for molecular design and chemical synthesis planning. His research interests are in computer-assisted scientific discovery, algorithm development in computational chemistry and AI, and applications in organic synthesis and drug discovery. Dr. Timur Madzhidov is a senior product manager for Reaxys at Elsevier, and in his role at Elsevier, Timur supports projects to improve search and predictive capabilities and the readiness of Reaxys data for AI and ML applications. Prior to joining Elsevier, Timur had academic positions in chemical robotics, chem informatics, and molecular modeling, and is a recognized chem informatics researcher. Timur has co-authored over 70 scientific publications in the fields of reaction informatics, AI application in chemistry, algorithmic chem informatics, and chemistry-aware machine learning. Today, Marwin will be presenting a talk titled Accelerating Design Make Test Cycles with AI. Welcome, Marwin and Timur. The stage is yours.
Yeah, thank you for the kind introduction and also the invite. It's really great pleasure to be here with you. Yeah, small molecules are very important for basically everything in our lives. They change the way we live and die. As agrochemicals, they help to feed the world. As materials, as organic materials, they help to improve the quality of our lives. And as drugs, they help keep us healthy and live long. But discovering new molecules is very expensive. And a large part of the discovery expense is in the first phase, and especially in drug discovery, before going to the clinic. And that makes the discovery of new drugs especially unnecessarily complicated and expensive. And what can we do about that with the help of AI? And AI is a big topic, is a big name. The way I like to think about it is that it is a complementary pillar to experiment and to simulations, quantum mechanical theory, and chemoinformatics. And in the end, a helpful additional pillar to solve the very hard problems that we have to solve in chemistry. So it adds to what we already have. And what I'm going to do is to walk around the cycle of molecular discovery through, which is usually conceived as analyze, make, design, make, and test. Because AI in various forms is starting to impact all of the steps in this cycle. In the forms of analyze, for example, as human-in-the-loop learning, design using generative molecular design, make by synthesis prediction, and for testing we have QSA, for example, machine learning-based property and bioactivity prediction, but increasingly also accelerated simulations where we use AI to accelerate, for example, classical MD simulations, or even completely replace MD simulations with generative AI. And one example or two examples actually for those are the recently published BioEmo model by colleagues of mine from Microsoft that allow us to do what traditionally could only be done with molecular dynamics, but in a much accelerated way using generative models to go to ensembles, for example, of biomolecular structures. And the recently published also Boltz-2 model that allows, again, for example, to do both biomolecule, small molecule complex prediction, and even allows to do something like accelerated bioactivity predictions that rivals the accuracy of FEP calculations. Now I'm going to talk about generative design. So if we design molecules, we actually don't care so much about the molecular structures themselves, but care about the properties that these molecules have. For example, biological activity, and then all the other properties that you need, for example, to have a drug or a catalyst or a functional molecule in many other ways. Usually one thing we need, if we want to design molecules, we need a way to predict their properties. This could be a model, this could be a simulation. I just leave it at that. Something that taking a structure gives us, allows us to predict the property or the property profile that we care about. And one computational approach that we then can take is virtual screening, where we screen loads and loads of molecules in the shotgun principle, and in the end pick the best of the existing molecules that we screened. And the other approach, which is called de novo design, generative molecular design, or inverse design, is where we have not just a molecule generation algorithm which generates molecule on the fly, but then also some kind of optimization algorithm that tries to find us an even better molecule by navigating the chemical space and shifting it into a better direction, which then allows us hopefully to find molecules that maximize the property that we care about or optimize the property that we care about, but potentially, because we're not screening extensively, potentially has in the risk of missing property hotspots as a trade-off. But in contrast, then allows us to explore much larger chemical spaces. And the way to generally think about is that we have a molecule generation algorithm that's generates molecules, that coupled to a scoring function. A scoring function tells us how good this molecules are, and then this allows the molecule generating algorithm to again shift into a more promising direction. So you can, from a computer science perspective, call that combinatorial optimization. Now the question is, what molecules do we want to actually generate? And on one end of the chemical space, we have local libraries, like an HTS stack. We have virtual screening libraries which are enumerated, and on the other far end, we can, in a completely unrestricted way, combine atoms and bonds, which is kind of the largest chemical space you could think about, which is larger than the number of atoms in the universe, of course. But the issue is not just the size of the chemical space, but it's also another axis, that's accessibility. So we need to be able to synthesize the molecules. The molecules need to be stable and, last but not least, not reasonable as well. And if we restrict the size of the chemical space too much by staying, for example, with virtual screening libraries, we get molecules which are very simple, that may be useful at early stages of drug discovery, for example. But it's maybe too narrow. And then if we go too unrestricted, we combine molecules in our atoms, bonds in an arbitrary way, we get nonsense molecules like these, which are not very useful, obviously, or especially for computational chemists. If you show these molecules to medicinal chemists, too often they will stop working with you. It makes no sense. But on the other hand, we need complex molecules. If we look at some of the molecules that go into the clinic, we see the complexity of these molecules increasing. So we need algorithms that can tackle the complexity of the molecules that do go into the clinic. So what's the sweet spot that fits right in between, that gives us accessible molecules and large chemical space access? And that is the emerging paradigm of generative models for molecules, which you can think about essentially like nowadays ChatGPT for molecules. We have a model, an AI model that grows the molecule step by step in various different ways. Like an LLM would generate a sentence, or by stitching together letters and words, we can stitch together molecules by predicting atoms and bonds step by step. And we can use such models, train them on large data sets of reasonable molecules, for example, Campbell, train our generative model, and then generate new structures. that surprisingly works very well. We can generate new reasonable structures that resemble, for example, if we train drug-like molecules, resemble drug-like molecules. Now, this alone is not very useful. We need to steer these models, and this we can do either by fine-tuning on molecules which we already know are good. For example, if we already have identified hit molecules, we can fine-tune our generative model on that to give us more of what we already know is good. And we can use reinforcement learning, where we couple this generative model, this pre-trained generative model, with a scoring function to steer it in a promising direction. And yeah, in the past, we've used it for a number of several use cases, let's say for in the benchmarking way, for example, shown that these models can rediscover actual molecules that had been designed, for example, against Staphylococcus aureus, for example. And now in the last couple of years, there have been a plethora of new models, new generative models for molecular design. So you can really pick and choose the model that you like. They all work by now, or can work pretty well if you know what you're doing. There are also by now a number of prospective studies out there using generative models to design molecules. Many of these use this autoregressive reinforcement learning paradigm, which I described. For example, there's very nice work by Daniel Merck and Francesca Grisoni designing molecules for nuclear receptor targets, reaching up to nanomolar activities, synthesized and validated, tested in their labs. Another example here from Yang et al. Using a generative model to design an initial hit against two different targets with nanomolar activities, essentially, and then took these AI-generated molecules to lead optimization and even eventual in vivo testing in that paper. And an example from us where I was involved, using a generative model coupled against a scoring function that's using let's say physics-based method, docking in this case. Nowadays, you would probably use something like Boltz-2, and that generates molecules, scores them with a docking, for example, in this case, and then has some other scorings for synthesizability and drug likeness included. And then we took the most promising molecules for in vitro validation, and got as a proof of concept for these designed these SEH2 inhibitors, finding promising micromolar ligands here, and identified a new scaffold that wasn't present in the literature before. Now the big question is, how can we make these molecules? And I like to think about AI-based synthesis like a satellite navigation for molecules. We care about going from A to B, from our target to the building blocks efficiently. And what we must always not forget that these models provide a suggestion. We need to drive ourselves, and maybe there's some, let's say, potholes in the road we have to drive around. We have to make sure we're driving safely. The AI can't do that for us yet. So conceptually, computer-aided synthesis planning is very simple. We just need a module to propose feasible retrosynthetic disconnections. So given the target molecule, predict us possible reactions that lead to that target in one step. We need an efficient search algorithm that can navigate large retrosynthetic trees. And we need the stop criteria, the building blocks, for example, and ranking criteria for our routes. Now, computer-aided synthesis planning had a very, very long history, going back to the 1960s, to Vleditz and Corey, and Ugi, and over the decades, loads of different approaches, most of them based on logic and expert systems, had been proposed. But until, let's say, the mid 2010s, the field was really at a dead end in a way, going back to this paper from '96 from Garsteiger. And this is when we started to work on this topic. And if you want to understand why synthesis, a planning algorithm, is actually challenging, we can go back to Corey, actually, who tried to encode all of chemical knowledge in a logic form, which turned out to be great for humans and got him the Nobel Prize, but didn't work so well for the machines. And I'll give you 2 examples why it's difficult. First of all, we need to not just encode, let's say, the retrosynthetic disconnection. So, for example, we have 2 rules here, Suzuki and Komada, to make this aryl-aryl bond. But for this molecule, we couldn't apply the Komada rule because there would be a side reaction of the Grignard reagent with the aldehyde. So we would also need to additionally include that information, that there's a reactivity conflict. And if you do that, the rules that you have to encode become very, very complex very quickly. And often the scope of reactions isn't really well understood and quite often subtle. And then the other important point of where rules don't really help you is in how you prioritize disconnections during synthesis planning. If you look at a molecule like this, there's only one really feasible retrosynthetic disconnection, which is making the ester, obviously. You could probably chemically also make this molecule by some kind of cross-coupling and building up this alkyl chain, but it wouldn't really make sense to try that first in your retrosynthetic analysis. So getting this intuition into the machine is very tedious, but chemists learn it by looking and studying chemistry. So how can we get the computer to do that? And finally, the number of chemical reactions grows exponentially, and we need our algorithms to be quickly adapted to the latest new reactions that come out in the literature very quickly. So we need a scalable approach that can handle that, because it's not just that chemists publish the same chemistry all over again and again, but they also publish new chemistry. So here you see the number of unique reaction types published each year, which also grows exponentially. So what we did a couple of years back already to introduce the concept was use machine learning and reinforcement learning for this problem. So learning retrosynthetic disconnections, learning to predict reactions, using modern search algorithms, and then also using ML and its metrics framework to improve these algorithms. Conceptually, again, this is very simple how this works under the hood. We take the molecule, we have an AI model, deep neural network, where the molecule gets encoded, passed to the network, and then it predicts the retrosynthetic disconnections, and the most likely ones we can then use, apply, for example, if we have if we take the specific approach, predict the most likely rules or named reactions to make this molecule, apply them to the starting product, and get the precursors, and then can repeat these analyses over and over again. Now, how do we test the quality of such a system? We can ask chemists. So we show chemists routes predicted by the system, predicted or taken from the literature, and then see whether they prefer one over the other. And it turns out in our analysis for, let's say, molecules of medchem complexity, we found the chemists don't show preferences over the literature routes. They perceive the predicted routes as equal to what came out of the literature. So that was a pretty nice finding. Here's an example molecule example analysis, taking 6 seconds to solve with an AI. For me, which is take more than 6 seconds just to look up the building blocks, of course. Now, yeah, there are a number of really, really great papers and researchers in this space. I want to highlight these 2 papers from Kohli Group and Schwaller that take this to even further levels. And now we have ML-based synthesis planning increasingly used by industry and integrated into for example, Reaxys, which Timur will talk about in a bit. Now, what's next? What we want to do now, or what we are working on now, is how do we improve these models further. And We have released a package called Synthesis for that, which you can check out, which is a metrics and also model implementation framework, more, let's say, for researchers at this point, which we use to improve these synthesis models, and especially improve these synthesis models for reactions that are not so frequent, which are important, let's say, from a strategic side. And I'll show you a few examples in a second, because the current models don't work well for, let's say, rare reactions, which actually make up the majority of the reaction databases. We have published that. You can check our paper on arXiv. It's a new model that combines multiple machine learning models together, aggregates the predictions, and what we found was that the new model is much more robust than the established models that are currently most widely used, up to 20% more robust, especially once the molecules get a bit more exotic, more different to what the model has seen before. And also the models are very fast, so and allow to solve much more molecules, let's say, in chemoinformatics workflows. So let's say solving again 20%, 30, 40, 50% more molecules, depending how fast you need these algorithms to be compared to the current models. So that's where things are going. And to show you one example of a route where the model predicts a rare reaction that maybe you wouldn't think about as a chemist first. For this route, it predicts this Hammersberger-Knittel indole synthesis, which at least I wouldn't have thought about first when looking at this molecule. And yeah, these models can now routinely predict long sequences of routes. And yeah, check our paper for a bit more background information and more routes. So where's this all going? AI will permeate basically every aspect of chemistry in the same way as large language models have done that in a very short amount of time. AI tools can be very helpful to address hard problems, but I think they're most useful in the hands of very experienced chemists that have also the domain expertise to interpret and use the results. What I find quite remarkable is that the progress is naturally integrated into workflows. So, but it's more about in a so what way. So in the way that we can now have an LLM write coherent text and say, so what? We take it for granted, even though it's actually mind-blowingly amazing that this is possible. We start to have AI tools that just completely design chemical syntheses from scratch, and we take it more or less for granted. And overall, I think this will mean that the role of the chemist will evolve to higher level and more strategic tasks. And yeah, we'll look back to the time when let's say we had to go to the library and take out a journal paper publication to read it. And in the same way, we might look back at route design. And similarly, we have AI tools that point us to the right places in literature to make our decisions. Yeah, and with that, thank you for your attention.
Yeah, thank you, Marvin. And probably from this point, I will take over. Yeah, and it's a special pleasure to see Marvin today. Thank you very much again. And yeah, shout outs for very interesting presentation. And also, I want to show you some, in part, what the work of Marvin led to. That's why I'm so pleased to see him today on our call and be after him. So this publication, which Marvin already referred to and he mentioned, is about, so it's really changed the way how currently chemistry processes are being done in industry, because it's shown how artificial intelligence solution can be applied for synthesis planning, and that the solution which are based on artificial intelligence are now way better than any other. However, there is a long path between having good idea, having good presentation, publication, to really solution that can be used by every chemist in every laboratory, even those that are not very proficient with artificial intelligence solutions. And in Reaxys team, we are bringing AI solutions to life. For example, by combination of great technology, which was proposed and developed in part by Marwin, by big data, which are trustworthy, which contains all the bits of information required, and the great user experience, the solutions that are pleasant to use, and which provide all the required feedback. So this solution, which was developed by which was proposed by Marwin, we developed it inside Reaxys, train it on whole reaction data with the help of our partners company Pending AI, and that the solution, which is powered by Pending AI, we thoroughly tested. For example, we tested it with with the brilliant minds in the space of organic chemistry, with Professor Carrera and Professor Reaxys, who confirmed that the solution that the proposed routes are robust, and the user experience is friendly and intuitive, and that tool really provides time savings. And also, we of course extensively tested this solution. Our solution were extensively tested in companies like this work coming from Boehringer, and the presentation coming from Boehringer, where they shown that Reaxys retrosynthetic solution was better than everything than all other solutions they are tested with. And that's why we are very proud that Boehringer Ingelheim is currently a user of Reaxys retrosynthesis model, which is powered by Pending AI. But okay, with that said, let me show how it looks in real life. This is so basically, when you come into Reaxys, you have a few bars, and there it is actually available via retrosynthesis tab. So in retrosynthesis tab, you'll see you can start drawing by drawing new structure which you might be interested in. That could be any structure. If you want, you can insert name for this structure, for this compound, or smiles of it. Let me write just something. I just make something up, imatinib, and you'll see our system recognizes the structure for this compound. You can click on synthesize, and the synthesis of this compound will be run. Of course, you can do the same with the smiles. For example, you can insert structure from smiles and run another calculation with that, and it is very intuitive and very user friendly. And there are some additional parameters or features which you can select. For example, this total number of routes which you are going to see. Instead, if you want to have some ideas about how to decompose this molecule into bits, to have some ideas how this molecule could be synthesized in one step, you can click onto last step only. In this case, you'll see only one disconnection. And there are some parameters that define diversity of route, processing time. Standard time is most of the time, like 99% of cases, it's sufficient for having roots. And you can select between different building block libraries. We implemented, so in Reaxys, we have a quite extensive library of building blocks, which comprises 150 millions of compounds. And there are some sub-libraries. You can select only compound that are available within 10 days, so which are readily available, or you want to have all the compounds, or you can limit by price because, for example, this library is only compounds that are with a price within $10. So if you select only those, you will only see routes that end up with a cheaper building blocks. But of course, the more building block libraries you have, the more chances that you have a root. There are also another interesting, let me add some molecule. There are some other interesting features. Of course, you can draw a compound or modify the compound which you want, but there are also two features here. One is called break bond. So it is basically you prompt model what bond you want to break first. For example, you are only interested in routes which start from, say, breaking this ether bond. So in this case, if you click synthesize, the algorithm will first try to look for synthetic routes where this bond is disconnected first, and only then try to figure out how to synthesize the syntons for those compound. Or other way around, there is a button to protect certain bond. For example, if you don't want this bond to be broken, you want to keep it for the whole synthesis due to some reasons, you can protect this bond, and then the algorithm won't touch this bond ever in synthetic route. So this is a quite this might be important thing for you to consider when you trying different routes. Okay, so how the result will look like. So after you click the synthesize button, the projects are created. It takes some time for molecule to progress. You see, not that long ago, not that much, because, for example, while I was talking, this imatinib molecule, the synthesis routes were already found. So for imatinib, we found 20 predicted routes and 7 published ones. If you want, you can go through them, click, and so the algorithm will show you what routes are available. So all of them will be loaded. So since this calculation takes some time, we recommend, if you have some molecules or some ideas to validate, just enter a few of them, and that's probably and give a model some time to work on it. Yeah, sorry, I just decided to refresh in the wrong time. So you see, when you click on the routes, you see what building blocks are used for synthesizing these. You see that all building blocks are commercially available. You can hover over this card button and understand what was basically the prices of building blocks required for this synthesis of imatinib. So and this bit describes root topology. So basically how it looked like. So you see that, okay, this is one-step synthesis from this compound for imatinib. And of course, here are predicted routes for imatinib. Again, so some of them are one step, some have more complex topology. And so you can look through it. You can select based on prices, or if you want to see on this page, you can click on preview, see this, and see the full route. However, if you want to explore a bit more, you can click on preview, and you will go into a very nice representation of the full route in retrosynthesis. And here you see the molecule, the full retrosynthetic pathway for this molecule, and also for every step we provide the most similar examples in Reaxys from which you might have an idea what conditions are required to perform that reaction, and this is possible for every step. You can show for the second step. You see that the number of steps are given here, so you can have a look at every step, what are conditions there, and finally, of course, you can copy root and use it further and paste it, for example, into your editor. And finally, there are some customization capabilities. For example, if you consider this molecule as too complex and too expensive, you can click on this button, and if this molecule is published, you might look for reactions that synthesize this molecule from a more simple building blocks. For example, okay, there was one step synthesis from this building block, and this building block is way cheaper than the one reported there. So if you click on it, you added that that building block into to the synthesis. And finally, what I want to show is that in case you are using default settings, if in case of for some molecule routes cannot be found, for example, your molecule is too complex, the algorithm tries to modify settings in order to find a way to synthesize it. So we automatically try to adjust our settings to guarantee more chances to find something reasonable. So, and for some synthetic route for this molecule, for example, you see this molecule was not solved, then algorithm attempted to use extended processing time, change the diversity settings. Again, it failed to find the compound, but you see the compound looks really esoteric one. And even if in this case, if it doesn't help, then the algorithm tries to apply last step, only disconnections, and to have an idea maybe how to synthesize this compound, and in a more interactive way. So that's basically all I wanted to say to you. Thank you very much for your kind attention.
Thank you, Timur and Marvin, for your wonderful presentations. And it looks like Marvin got a head start with some of the questions being asked by the audience. However, there are a couple here I'd like to revisit over the next couple minutes. The first one, since AI output hallucinations, it's a hot topic, and I think it warrants a little additional discussion. There was a question from the audience about how do you address or minimize the risk of a hallucination or generation of wrong or unfeasible structures in generative chemistry? Marvin, do you mind answering that?
Yeah, sure. Great question. So first of all, yeah, I think if you really train your model well, they should already have a very strong baseline performance of giving you good structures. And I mean, I feel like the examples that we've seen sometimes in literature of where this happens is also caused by by people not training the models in the right way, using parameters which are tricky. So these models can be tricky to use, and require some expertise. But then generally the baseline performance of these models can be good, also as evidenced by, I don't know how many tens or hundreds of papers there are already out where these methods have been experimentally validated. But what's often very useful is to use additional chemoinformatics techniques to, for example, use rules to filter down problematic structures, exclude non-reactive groups, and then also to couple that with synthesizability scoring or synthesis prediction that again can remove sometimes problematic structures that come up.
Thank you, Marvin. We have time for one more question. I'd like to get both of your opinions on this one. And you started answering this already, Marvin. And the question is, which areas of chemistry benefit most from AI synthesis models? Starting with Marvin, please.
Yeah, so I think that different types of chemists have different uses for these models. So for computational chemists, using these in virtual screening and generative design workflows to filter down actionable molecules, depending on, again, on the stage in your drug discovery campaign, is very useful. For automated synthesis, it's very useful. For medicinal chemists, it's useful that you can, for example, find routes to building blocks which you would have never, let's say, considered to be available. But then, if your task is to make a certain molecule in a very fast amount of time, let's say with cost not being a constraint, you can let these systems suggest you building blocks which you just would have never thought about that they're available, for example. Then for process chemists, it's quite useful for route scouting to get, let's say, a very complete picture of what could be possible in terms of routes. So you get suggestions for routes that, again, maybe you wouldn't have considered, or just to make sure you have really the complete picture of what could be a possible route. So I think every group of chemists can benefit from these approaches in different ways.
Thanks, Marvin. Timur?
It's unfair because Marvin covered everything, almost everything. So just to add to what Marvin said, like, of course, these synthesis planning models can also be used in material science because, for example, some generation of ligands for material design is also sometimes important. Process chemists, for example, I know that quite often have a problem of synthesizing are identified. They need to make a sample of that impurity for further testing, for example. And in this case, of course, that models can be applied. So, but the rest Marvin already covered. So yeah, it is everywhere basically where the synthesis is of molecules is required. That synthesis model.
Looks like we had a little bit of a connection issue with Timur, but I'd like to thank you, Marvin, for your time. Timur, thank you for sharing your expertise with all of us. For our audience, again, there shall be a survey posted.
Yeah, thank you for the great discussion. And also, yeah, it was a great honor, especially to be on stage with Timur here, even though he got disconnected.
Thank you, Marvin. We'll be on shortly with our next set of speakers. Thank you so much.